Welcome to the Deep Dive. Today, we're going to be, diving into this pretty wild area of math. We're talking about p-adic unit disks.
Yeah.
Sounds a little intimidating, I know, but trust me, it's way more interesting than it sounds.
Right.
We're about to uncover some serious mathematical intrigue. Our guide for today's deep dive is, it's this paper by Elden, Elmanto, and Noah Riggenbach. It's called On the K-Theory of the p-adic unit disk.
Okay.
And, you might be thinking, K-theory, p-adic, what in the world are those? But don't worry, we've got you covered.
Yeah.
So think of K-theory as this kind of like this cool mathematical tool that lets us look inside like the hidden structures of shapes.
Right.
But instead of like, circles and squares, we're talking about shapes that are built out of numbers with really unique properties. So to help us unpack all of this, we're joined by our expert. So what's so special about the kind of math we're talking about today?
Well, I think a good way to think about it is like, it's almost like you're stepping into a mathematical hall of mirrors, right? So we're dealing with these things called perfectoid rings, and those are these sets of numbers that basically like bend and twist the usual rules of arithmetic. Like imagine a number line where addition and multiplication work in these totally unexpected ways.
Okay.
Like we've got this secret code, mathematicians have cracked this code. And using that, we can kind of understand this whole new world of numbers.
Okay, so we've got our K-theory decoder ring here, and we're diving headfirst into this like funhouse mirror world of numbers. So what exactly are Elmanto and Riggenbach trying to figure out in this warped reality?
Yeah, so that's where it gets really, really interesting. They're kind of tackling this puzzle that's been, it's a head scratcher. It's been stumping mathematicians for a while. How does K-theory behave in something called the p-adic unit disk? So picture this. It's like, imagine a disk, but instead of it being made of, like points on a graph or something, it's built entirely out of these strange perfectoid numbers that we're talking about.
So it's like a shape, but the shape is made of bizarre rule-breaking numbers. Okay, this is already getting good, so tell me more.
All right, so here's the real head scratcher. Mathematicians Antio, Matthew, and Morrow. They discovered this really, really weird thing about these perfectoid rings.
Okay.
They found that even though these things are super weird and they're really complex,
Right.
they sometimes act shockingly similar to much simpler objects called regular rings when you view them through the lens of K-theory.
Really?
Yeah, so it's kind of like, it's like finding a secret passage connecting two completely different parts of like this mathematical universe.
Hold on. So we've got complex objects behaving like simple ones.
Yeah.
That's like discovering that a black hole acts just like a basketball sometimes.
It's kind of like that, yeah.
So Elmanto and Riggenbach, they picked up on this, right? They dove in to see what was going on with this mathematical plot twist.
Exactly, yeah. They wanted to kind of see just how deep this rabbit hole goes. And oh boy, did they find some fascinating stuff.
Okay.
So one of the things that they discovered, they found something called the Quillen-Lichtenbaum phenomena hiding within this p-adic funhouse.
All right, break it down for me. What is this Quillen-Lichtenbaum phenomena, and why should we be freaking out about it?
Okay, so imagine you've got like, two explorers, and they're charting different routes through this really dense, like, unexplored jungle.
Okay.
And suddenly they bump into each other in a clearing, totally by surprise.
What?
Yeah. That's kind of what this discovery is like.
Wow.
The Quillen-Lichtenbaum phenomena is this unexpected link between two concepts that you would really think are related. Topological cyclic homology, which is a mouthful, I know.
Yeah.
And then our old friend, K-theory.
So we've got these two like seemingly different mathematical paths that end up leading to the same destination.
Exactly.
Especially in this weird p-adic world.
Yeah.
It's like those explorers, they stumbled onto a shortcut that nobody even knew existed.
That's a great way to think about it. And what makes it even more exciting is that this shortcut wasn't just a lucky break or anything.
Right.
Elmanto and Riggenbach, they actually found that. There are specific rules and conditions that govern when and how this phenomenon works.
Wow.
And this is where their two big discoveries come in. Theorems 1.1 and 1.2.
Okay, this is serious. Let's start with theorem 1.1. What's the big reveal there?
Okay, so theorem 1.1, this theorem kind of dives into the specifics of this, like this shortcut, this Quillen-Lichtenbaum phenomena.
Right.
It basically tells us that it's not just some random occurrence.
Yeah.
It actually depends on some key factors.
Yeah.
Like smoothness and relative dimension within the p-adic unit disk.
Wait, smoothness? Is that like saying a shape can't have any sharp corners for this shortcut to work? And what even is relative dimension in this context? I need some help here.
Okay, yeah. So imagine you're like drawing a shape, right?
Okay.
If the lines you're drawing have to flow smoothly without any like abrupt changes in direction, we can kind of think of that shape as being smooth.
Right.
In a way, Theorem 1.1 basically says that for the Quillen-Lichtenbaum phenomena to work, the mathematical spaces involved, they need to be smooth in a similar way,
Yeah.
without any sudden jumps or breaks.
So no sharp corners allowed. That actually makes a surprising amount of sense, even for, my non-mathematician brain. But
Yeah.
what about relative dimension? That sounds even more
Don't
complicated.
worry, it's not as scary as it sounds. Think of it this way. Imagine a flat piece of paper,
Right.
right?
Okay.
You can move your finger, like up and down, left and right. That's 2 dimensions.
Right.
Now imagine a perfectly straight line drawn on that paper.
Okay.
You can only move your finger back and forth along that line, right?
Right.
That's 1 dimension.
Okay.
So the line, in relation to the paper, has a relative dimension that's 1 less than the paper itself. It's all about, like, how much room a shape has to move around inside another shape, so to speak.
Okay, I think I'm starting to get it. It's like a hierarchy of dimensions, and for this Quillen-Lichtenbaum magic to happen, the dimensions need to, like, line up in a certain way.
You got it.
Okay.
Now, ready for Theorem 1.2?
Hit me with it. What does this one tell us?
Okay, so while Theorem 1.1 lays down, like, the law of the land,
Right.
Theorem 1.2 is where things get really, really exciting.
Okay.
At least for, us math nerds.
Right.
Theorem 1.2, it gives us a concrete way to actually calculate the K-theory of the p-adic unit disk over a specific type of curve.
Wow.
Using something called, get ready for it, symptomic cohomology.
Whoa, hold up. Symptomic cohomology, you're going to have to pump the brakes and explain that one.
Okay.
That's a new one.
So think of it as another like specialized tool in the mathematician's toolkit, just like K-theory helps us understand hidden structures. Symptomic cohomology lets mathematicians study like equations and their solutions.
Yeah.
Within this bizarre p-adic world.
So it's like having X-ray vision for equations.
Yeah, that's a great way to put it.
Okay, so how does this symptomic cohomology X-ray vision, how does that help us understand the p-adic unit disk?
All right, so what Elmanto and Riggenbach showed
Yeah.
is that there's this direct connection between certain K-theory groups of the p-adic unit disk and these specific symptomic cohomology groups. They found a hidden doorway that links these two like previously separate rooms in this vast mathematical mansion.
So by using symptomic cohomology to like peer into one room, we suddenly get all these insights into what's happening in the other room, which in this case is the world of K-theory and the p-adic unit disk.
Exactly. And this connection is kind of a game changer, right?
Right.
Because it lets mathematicians translate information back and forth between these two different areas. And that leads to a much deeper and more kind of, nuanced understanding of both.
Right.
It's like we've got this like bilingual dictionary that's letting us unlock the secrets of 2 different languages.
This is blowing my mind. Who knew that diving into the world of p-adic unit disks would be like stepping into a mathematical Star Trek episode?
Yeah.
We've got like parallel universes, hidden dimensions, secret codes waiting to be cracked.
It's true. It's pretty wild.
And like any good Star Trek episode, there's always more to explore, right?
Oh, absolutely.
We've been focusing a lot on the p-adic unit disk itself, but, we mentioned earlier that it exists over a curve. To really appreciate like the full implications of this paper, we need to kind of dig into what that means, right?
Yeah, definitely.
So we're going even deeper into this mathematical rabbit hole. What kind of curve are we talking about here, and why is it so important?
All right, so when we say curve in this context, we're talking about a very specific type of mathematical curve. It's called a smooth affine curve.
Of course, it's math, so we can't just say curve. It has to be smooth and affine. I'm picking up on the lingo here. But seriously, what makes these curves so special?
Okay, so think of it this way. Imagine you're drawing a line on a piece of paper. If you can draw it without lifting your pen and without any sharp corners or like sudden turns, that's what we call a smooth curve.
Okay.
An affine curve just means it follows certain rules in terms of like, how its equations are written.
So it's like the difference between a perfectly flowing ribbon and like a jagged piece of string. Yeah. Okay, I'm with you so far, but how do these smooth and flowy curves, how do they play into all of this p-adic unit disk stuff?
Right, so that's where Elmanto and Riggenbach's work. That's where it gets even more precise.
Okay.
They found that when you're dealing with a p-adic unit disk, over one of these like smooth, well-behaved curves,
Mm-hmm.
you can actually write down very specific formulas to calculate its K-theory groups. It's like they've given us this set of keys to unlock even more secrets within this already mysterious mathematical landscape.
It's all about finding those hidden connections, right?
Exactly.
Like those mathematical trap doors that lead to unexpected insights.
Precisely. And what's so remarkable is that these connections, a lot of times they have implications far beyond just like the specific problem that they were originally designed to solve.
So even though we're talking about this really niche area of math here, p-adic unit disks and all that, its impact could be felt in like completely different fields.
Oh, absolutely. Yeah.
Yeah.
That's the beauty of mathematics, right? It's all interconnected. So like a discovery in one area can totally spark this like chain reaction of breakthroughs in fields that you wouldn't think are even remotely related.
Wow.
Who knows, maybe someday. Like understanding the Quillen-Lichtenbaum phenomena in the context of p-adic unit disks, maybe that'll give us a better understanding of how the entire universe is structured.
Okay, now that's a thought-provoking way to end our deep dive today. We've gone from, like, decoding secret mathematical languages to exploring hidden dimensions. And now we're pondering the structure of the universe itself, all thanks to this one paper about the K-theory of the p-adic unit disk.
It just goes to show there's never a dull moment when you start exploring the world of mathematics.
I love it. Big thanks to all of our listeners for joining us on this wild ride through the fascinating world of, pretty advanced math. And a huge shout out to Elden Elmanto and Noah Riggenbach for their awesome work. They're the real explorers here.
They're paving the way for a whole new generation of mathematicians to kind of, push the boundaries and unravel all these mysteries that are hidden within these abstract spaces.
Until next time, keep those brains engaged.
Yeah.
And never stop exploring the infinite wonders of mathematics.
All right, so, brace yourself because we're about to get really technical here.
Okay.
Their paper reads like a who's who of, advanced mathematical tools. They use something called topological cyclic homology. No surprise there,
Right.
given our Quillen-Lichtenbaum discussion. But they also used motivic filtration and prismatic cohomology.
Okay.
And those are not exactly concepts you'd just casually chat about at dinner.
Okay, I have to admit, even I'm struggling to keep up now. Can you, give us a sense of what these tools are like? Maybe a little less advanced mathematics textbook and a little more, explain it to me like I'm a curious tourist who accidentally wandered into the wrong lecture hall.
Okay, all right, challenge accepted. So imagine you're trying to understand a really, really complex machine, right?
Okay.
Like let's say a really high-powered engine or something.
Right.
Motivic filtration
Right.
is kind of like having this set of really specialized tools that lets you break that engine down into like, all of its individual components,
Okay.
layer by layer.
Right.
It's kind of like, it helps mathematicians dissect these really abstract mathematical structures and understand how each little piece fits together.
Okay, I think I'm starting to get a picture of that one. What about prismatic cohomology? That one still sounds a little intimidating to me.
All right, so think of prismatic cohomology as like almost like a set of really, really powerful lenses,
Okay.
that allow mathematicians to study the engine running under like, all these different conditions.
Yeah.
It's kind of like, if you could change the lighting in a room to highlight different features of a sculpture or something,
Interesting.
you can kind of think of prismatic cohomology like that.
Okay, so they've got their, metaphorical wrenches.
Yeah.
And their fancy lighting system. What does that let them see in this p-adic unit disk engine room?
Right. So these tools basically allowed them to like peer deeper into the p-adic unit disk than anyone has ever been able to before. And they were able to, really start to like identify the specific conditions that make the Quillen-Lichtenbaum phenomena work, right? And they even they figured out how to make like concrete calculations about the K-theory of certain types of p-adic unit disks.
Okay, so they've got their tools, they've made their calculations. It's all very impressive. But you know how I'm alive. I always want to know, so what?
Right.
Like, why should we care about these mathematical discoveries? What do they actually, change in the world?
You're right to ask that.
Mm-hmm.
It's not just about, writing down fancy equations or dealing with these really abstract concepts.
Right.
Even though it seems like we're miles away from any kind of practical application, when we're this depth in theoretical mathematics, history has shown us time and time again that these kinds of discoveries can have these ripple effects in fields that we might not even be able to imagine right now.
I love when you say that. It reminds me of that famous quote. It is impossible to be a scientist without realizing that one is in the presence of mystery. And it sounds like, Elmanto and Riggenbach are definitely onto some mysteries here.
Totally, yeah. Remember earlier we were talking about perfectoid rings and how they sometimes act like these much simpler regular rings?
Yeah.
Well, that kind of unexpected connection, right? That could be insanely powerful.
Yeah.
It basically lets mathematicians take all this knowledge and all these techniques and kind of transfer them between totally different areas of math. And that can lead to all sorts of breakthroughs in fields like cryptography, coding theory, even physics.
It's like that saying, all roads lead to Rome.
Right.
But in this case, it's like all these different mathematical paths are unexpectedly intersecting in this p-adic unit disk.
Totally.
And that's opening up all these new ways to understand the universe.
Exactly. For example, if we have a deeper understanding of K-theory, thanks to these discoveries like the ones in this paper, that could lead to more efficient algorithms.
Right.
For cryptography.
Yeah.
Which can make all of our online transactions even more secure, right?
So the next time I'm buying something online, I can thank Elmanto and Riggenbach for keeping my credit card information safe. Not bad for a couple of mathematicians just exploring the p-adic unit disk.
Not bad at all. And honestly, this is this is really just the tip of the iceberg. Their work is kind of shining a light into a previously unexplored cave.
Right.
Who knows what other wonders are waiting to be discovered in there?
That's what I find so exciting. We've been, talking a lot about the big picture, the potential impact of all this, the mysteries that are still out there to be solved. But before we, wrap things up here, I'd love to maybe dig into a really specific example from the paper, something really concrete that really illustrates, the power of these findings. Do you have anything in mind?
Absolutely. So you know how we were talking earlier about theorem 1.2?
Right.
And how it lets us calculate the K-theory of the p-adic unit disk over a curve using symptomic cohomology.
Right, right.
I think it'd be worthwhile to kind of revisit that for a second because it's a really, really great example of how, even though these concepts seem super abstract at first, they can have really, really real intangible implications.
You read my mind. I was really hoping we could circle back to that symptomic cohomology thing. Can you, refresh our memory on what exactly that is and how it all fits into this?
Yeah, totally. So think of symptomic cohomology as almost like a way of looking at equations and their solutions through a special lens, right?
Okay.
One that's really, really good at revealing these hidden patterns. In the world of p-adic numbers, it's kind of it's almost like having X-ray vision for these equations. Lets mathematicians see things that would otherwise be totally invisible.
Okay, X-ray vision for equations. I like it. So how does this symptomic cohomology X-ray vision, how does that help us understand the p-adic unit disk?
So what Elmanto and Riggenbach showed is that there's this really direct connection between these certain K-theory groups of the p-adic unit disk and then these specific symptomic cohomology groups. Okay. It's almost like, if you found a hidden doorway that links these two previously separate rooms in this giant mansion,
So by using symptomic cohomology to peer into one room, we suddenly gain all these insights into what's happening in the other room.
Exactly.
Which, in this case is the world of K-theory and the p-adic unit disk.
Precisely. And this connection is really, really crucial.
Okay.
Because it lets mathematicians, translate information and techniques between these two areas.
Right.
And that's what leads to a much deeper and more nuanced understanding of both of them. It's like having this bilingual dictionary that unlocks the secrets of two different languages.
This is blowing my mind. Who knew that diving into the world of p-adic unit disks would be stepping into a mathematical Star Trek episode, complete with parallel universes, hidden dimensions, and all these secret codes just waiting to be cracked.
I know, right? It's pretty wild.
It's amazing.
And, just like a good Star Trek episode.
Yeah.
There's always more to explore. We've been, talking a lot about p-adic.
Right.
The p-adic unit disk itself.
Right.
But if you remember, we mentioned earlier that it exists over a curve.
Right, right.
So to really appreciate the full implications of this paper, we have to kind of understand what that actually means.
Ooh, good point. We're going even deeper into this mathematical rabbit hole. What kind of curve are we talking about here, and why is it so important?
Yeah, so we got to talk about the curve.
Yeah.
Now, when we say curve in this like really specific mathematical context, we're talking about this very specific type of mathematical curve. It's called a smooth affine curve.
Of course, it's math, so we can't just say curve. It's got to be, you know, smooth and affine. I'm learning the lingo here. But really, like, what makes these curves so special?
Okay, so let me try to explain it this way. Imagine that you're like drawing a line on a piece of paper, right? If you can draw the line without like lifting your pen at all, and you don't have any like sharp corners or like, you know, sudden turns or anything like that, then that's what we call a smooth curve.
Okay, that makes sense.
And affine just means, basically it means that it follows certain rules.
Yeah.
In terms of like how we actually write out its equations.
Okay, so it's like the difference between like, you know, a perfectly flowing ribbon and then like a really jagged piece of string.
Exactly.
Okay, I'm with you so far, but how do these like, you know, these smooth, flowy curves, how do they play into all of this p-adic unit disk business?
Right, so that's where Elmanto and Riggenbach's work. That's where it gets like even more impressive. They actually found that when you're dealing with a p-adic unit disk over one of these like, you know, smooth, well-behaved curves, you can actually like write down very specific formulas that you can use to actually calculate the K-theory groups. It's almost like they've given us this like set of keys that we can use to like unlock even more secrets within this like already super mysterious mathematical landscape.
It's all about finding those like, you know, those hidden connections, those mathematical like, you know, trap doors that lead to like these totally unexpected insights.
Precisely.
Yeah.
What's really remarkable is that these connections, very often, they end up having implications that go way beyond just like the original problem that they were trying to solve in the first place, you know?
Oh, right, right. So even though this research is, you know, really focused on this super niche area of math, p-adic unit disks and all this stuff, its impact could actually be felt in completely different fields.
Yeah, absolutely. That's kind of the amazing thing about math. It's all interconnected. So like you make a discovery in one area and it could spark this whole chain reaction of breakthroughs in areas that you wouldn't think are even remotely related, you know?
That's incredible.
Yeah.
It's amazing.
Who knows? Maybe someday, like our understanding of the Quillen-Lichtenbaum phenomena, you know, in this context of p-adic unit disks, maybe that'll actually like help us better understand how the entire universe is structured.
Right. Okay, well, that's an amazing thought to end on. I love it. We started off like, you know, just trying to wrap our heads around this paper, and now we're like pondering the very structure of the universe itself. So big thanks to our expert for joining us on this wild ride today. And of course, a huge thanks to Elden Elmanto and Noah Riggenbach for their amazing work on this paper.
Absolutely.
You know, they're paving the way really for a whole new generation of mathematicians to like, you know, explore all these mysteries that are hidden out there.
Yeah, it's really inspiring stuff.
These like really abstract mathematical spaces. So to all our listeners out there, until next time, you know, keep those brains engaged and never stop exploring the infinite wonders of mathematics.
All right, so buckle up, because today we're taking a deep dive into a topic that sounds like, well, frankly, it sounds a little intimidating, p-adic algebraic K-theory. But trust me on this one, it's going to be a fun ride. We're going to break down some seriously cool math. We're diving headfirst into a brand new research paper, hot off the press, by Elden Elmanto and Noah Riggenbach. And it's all about, get this, p-adic numbers. And without getting too lost in the weeds, imagine like discovering a whole secret measuring system. One that lets you see hidden patterns in like shapes and spaces. Pretty wild, right?
It really is kind of like, imagine if instead of measuring with a ruler, right, you had this tool and it only told you how many times you could cut something in half. So like instead of saying this table is 3 feet long, you'd say, okay, it's 6/2 of a ruler long. That's kind of the basic idea here. We're basically using a different yardstick. And the crazy thing is this yardstick, it's based on these things called prime numbers.
I gotta say, that's a pretty cool way to think about it. So, okay, we got these new numbers, but what are these guys? What are Elmanto and Riggenbach actually doing with them? What's the big deal?
Well, they're looking at this, well, it's this fascinating pattern, right? And it's called the Quillen-Lichtenbaum phenomena. And it's like, okay, imagine you've got this super complex puzzle, right? And you can look at it two completely different ways. Like maybe one way uses colors and the other way uses shapes, you know? And then suddenly, bam, it's like you realize these two totally different views, they're actually showing you the same pieces of information. They're just doing it in completely different ways.
So it's like a mathematical Rosetta Stone. That's pretty wild. But I got to be honest with you, this paper, it's not exactly, what's the word, beach reading material. There's some pretty intense terms in there. I mean, whoa.
Yeah. Yeah. There's some serious math jargon flying around. Let's unpack some of it. Let's start with K-theory, right? So imagine, think of it like this. Think of it as a way to understand how you can cut and paste, like, pieces of a mathematical object without actually changing what it is. You know, like imagine you're trying to figure out the blueprint of a building.
So it doesn't matter how you rearrange the walls or whatever, the blueprint always tells you how the whole thing fits together.
Yeah, exactly. Okay, now, another big one, perfectoid rings. These things, they're like the smoothest, most symmetrical objects you can imagine in this mathematical world, right? They're like picture-perfect building blocks, and you can make all these complex shapes out of them.
Got it. So they're like what are those things? Those perfectly formed Lego bricks.
Yeah.
But for like the math universe.
Now, remember those p-adic unit disks we were talking about? Well, those are like specific types of spaces, but in this p-adic world. And Elmanto and Riggenbach, they're trying to figure out how this K-theory stuff, how it works within those p-adic unit disks. And they're finding some pretty wild results, let me tell you.
You got to give me more than that. Wild results. Come on. You've got me on the edge of my seat. What are we talking about here?
Okay, so to really get into it, we got to talk about another important thing here, and it's called symptomic cohomology. Now, stay with me here. It's basically like having these super powerful X-ray glasses, right? But for math. Like, mathematicians can put them on and suddenly see all this hidden structure within these p-adic spaces.
So they're seeing things that were totally invisible before.
Exactly. That's exactly it. And what they're seeing through these X-ray glasses is pretty amazing. They're finding these totally unexpected connections between this K-theory stuff and this symptomic cohomology, and it's changing how we understand these p-adic spaces altogether.
Dude, my mind is already blown, and we're just getting started. So tell me more about these unexpected connections. How are they actually, like, changing things?
All right, so one of the big findings of this whole thing, it has to do with something called the Segal conjecture. And this is where it gets a little complex, but stick with me.
Hit me with it. I am so ready for this.
So think of this Segal conjecture, right?
Yeah.
Like, it's a way to kind of measure how much information, how much of it makes it through when we put on those p-adic glasses, you know, those ones we were talking about. It's like, how much detail can we still see when we look at this mathematical thing through that lens?
So it's like, okay, so are we losing detail when we switch over to that different measuring system?
Yeah.
To those p-adic numbers?
Yeah, exactly. And what Elmanto and Riggenbach, these guys, they figured out that this Segal conjecture, when you use it on those p-adic unit disks, it's even stronger than we thought. It's like, imagine you find out your camera has this whole zoom level you never even knew about, you know? Like, there's hidden detail we didn't even realize was there.
Now, that is what I call a plot twist. What kind of hidden detail? Give me the good stuff.
So get this. They found that even when you do all this math stuff that you'd think would make things blurry, you know, you can still bring back, like, a surprising amount of the original information. It's like, okay, imagine you take a blurry picture, right? And you didn't think there was any way to fix it, but then bam, you enhance it and boom, you see all this detail nobody thought was even there.
That's pretty incredible when you think about it. But okay, so how does this change things for mathematicians? What's the big takeaway?
It's telling us there's a good chance, a really good chance, that we've only scratched the surface of how all these mathematical tools, how they actually fit together. Like, there are these hidden relationships, these deeper connections that we're just starting to see. Like, we're discovering, like, this whole network of tunnels under a city we thought we already knew, that kind of thing.
So it's not even just about the equations themselves. It's more about the big picture.
Right. You got it. That's exactly it. This is the kind of research that, like, blows the roof off of pure mathematics, you know, and it opens up all these new paths for other fields, too.
You know what? It's funny because we started off talking about these p-adic numbers, which, let's be real, sounds super abstract. But you're telling me that there are implications beyond just, like, theoretical math.
Well, absolutely. I mean, history's full of examples where these super abstract mathematical ideas ended up having huge real-world impacts. Like, think about number theory, right? I mean, it sounds pretty out there, but that stuff is the backbone of modern cryptography. And you know what that means? That's what keeps all our online transactions safe.
That's why. I mean, that's a huge impact for something that started out in the math department.
Tell me about it. And the best part is we have no idea what practical applications this p-adic stuff might have. I mean, we're talking about a deeper understanding of how numbers work, right? That's the thing about science, about exploring the unknown. You just never know where it might lead.
Now I got to ask, how did they actually prove this result about the Segal conjecture? Did they use any, super cool techniques or anything like that?
Oh, they did. They definitely did. They used this really clever thing called prismatic cohomology. And I know, it sounds super intimidating, but it's actually pretty elegant when you get down to it.
Okay, I'm listening. Tell me more.
Okay, so imagine you have these glasses, right? But they're not just any glasses. These glasses let you look at a mathematical object, and you see it from multiple angles all at the same time. It's like having multidimensional mathematical vision. That's what prismatic cohomology does.
Okay, now I kind of see why you called it elegant. That's a really cool way to think about it.
Right. And these guys, they use this tool, this multidimensional vision, and they figured out how to build this bridge. And this bridge connects two totally different mathematical worlds. It connects the world of K-theory and the world of symptomic cohomology, which just so happens to be perfect for studying these p-adic numbers we've been talking about.
So wait, hold on. They connected two different areas of math to get this result. That's pretty wild.
They basically found a secret passageway, a way to, translate information between two worlds. That's what makes math research so cool. You never know what you're going to find.
It really is like finding a hidden connection between two historical events that seemed totally unrelated,
Speaking of exciting, you mentioned something before about a vanishing phenomenon that we were going to talk about.
Oh, yeah. And it's all tied to those p-adic unit disks and the connections they found. You ready for this?
Dude, you already know I am. Hit me with it. So wait, let me get this straight. You're saying that there are parts of these p-adic unit disks, and when you look at them through these, mathematical glasses, they just disappear.
Yeah, it's kind of like that, yeah. Remember how we talked about K-theory being like a blueprint for a mathematical object? Well, it turns out that certain parts of this blueprint, when you look at them through the lens of symptomic cohomology, they just vanish. Poof, gone. Okay, I got to be honest. I'm having a little trouble wrapping my head around this one. What does it even mean for a mathematical blueprint to just, disappear?
So it means that there are these mathematical values, right? And we'd expect them to be super complex and tell us a lot about the object, but when we look at them in this specific way, they just become zero.
Hold on, so it's like looking at a blueprint for a building and, realizing a whole floor is missing.
You got it. That's a fantastic analogy. And what's so fascinating is that this vanishing act, it's not random at all. It actually shows us this deep connection between the K-theory and the symptomic cohomology of these p-adic unit disks. It's like they're tied together somehow.
So this vanishing thing, it's actually a clue. It's telling us something important about these mathematical objects.
Bingo. It tells us that these two ways of looking at p-adic spaces, K-theory and symptomic cohomology, they're even more deeply connected than we thought. It's like finding a secret passage that connects two rooms that seemed totally separate before.
This is blowing my mind. So what's next? What are the big implications of all this? Where do we go from here?
Well, the coolest part is that it opens up a ton of new questions. We've only just scratched the surface of this whole vanishing phenomenon. We've only looked at it in one specific context, right? So what happens if we change things up? What if we tweak the parameters? Does it still vanish, or do we get some new crazy patterns? That's what's got mathematicians so excited.
It's like this research paper just opened a door to a whole universe of unexplored mathematical ideas. Wild.
That's exactly what it is. Elmanto and Riggenbach's work, it's really pushing the boundaries of what we know about p-adic algebraic K-theory. And honestly, I think this is just the beginning. We're going to see a lot more breakthroughs in this area, mark my words.
Oh, I can't wait. It's going to be amazing to see where this p-adic stuff takes us next. Thanks for being here and walking us through this incredible deep dive. I always learn so much from you. And there you have it, listeners, a glimpse into the incredible world of p-adic numbers, where even zero can lead to some seriously big discoveries. Until next time, stay curious out there.
Ever feel like the more you learn about math, the weirder it gets?
Yeah, definitely. It's like you reach a point and then suddenly, bam, you're in a whole other dimension of weird.
Totally. And today, we are diving into a paper that definitely takes us there. It's called On the K-Theory of the p-adic Unit Disk by Elden Elmanto and Noah Riggenbach. And let me tell you, it's a wild ride. Luckily, I've got our expert here to help us unpack it all. So this paper dives headfirst into p-adic numbers. Can you give us a crash course? What are those, and why should we even care?
P-adic numbers. Oh man, there's something else. Imagine a clock, but instead of the usual 1 to 12, you've got like only prime numbers on it. That's kind of how p-adic numbers work. They totally change how we measure the distance between numbers.
Okay, I'm trying to wrap my head around this. So instead of our regular number line, we've got one based on, say, the prime number 5. What difference does it actually make?
Well, it means that in this 5-adic world, a number like 10 is considered closer to 0 than 6 is.
Oh, wait, really?
Yeah, because 10 is divisible by 5. It's a totally different way of thinking about closeness, about what it means for numbers to be near each other.
Wow, okay, you're definitely messing with my intuition for numbers here.
Okay.
Now, the paper also throws around this term, p-adic unit disk. What exactly is that?
Right, so think about a normal unit disk, the kind you probably remember from geometry. It's got all the points on a plane within a certain distance, 1 unit from the center.
Right, I remember that.
A p-adic unit disk, it's similar, but it uses this wacky p-adic distance we were just talking about.
So it's like a regular disk, but warped by this bizarre p-adic distance.
Exactly, you got it.
But why is this important? What are Elmanto and Riggenbach actually trying to figure out with all of this?
They want to understand something called the algebraic K-theory of a line over this p-adic unit disk.
K-theory. All right, you're going to have to break that down for me.
Basically, think of algebraic K-theory as a set of tools, right? And mathematicians use these tools to understand the shapes and structures that are hidden within abstract math objects.
So they're using these unusual numbers, these p-adic ones, and this unit disk to explore some really fundamental math concepts.
Yeah, exactly. And to do that, they rely on another fascinating concept, perfectoid rings.
Perfectoid rings. I'm not even going to pretend I know what those are.
They're a bit of a mouthful, aren't they?
Yeah.
Just think of them like bridges. Bridges connecting different areas of math.
Bridges, okay.
They've got these properties that are kind of similar to certain special fields in math, and that lets mathematicians translate problems from more complex areas like rings into these simpler fields.
So are they kind of like Rosetta Stones, helping mathematicians decode these really complex problems by looking at them in a simpler way?
You got it. And in this paper, these perfectoid rings, they're essential. They provide the foundation for even beginning to study the p-adic unit disk.
Man, this is already blowing my mind, and we're just getting started.
So the paper, it dives into this big question. What does the algebraic K-theory look like for a line? Like, imagine a simple line, the simplest graph, over this p-adic unit disk we're talking about.
Okay, I'm with you.
And what they find is, well, pretty surprising, actually. They discovered that this line, it doesn't quite behave how you might expect it to.
How so?
It actually reflects this pattern, something known as the Quillen-Lichtenbaum phenomena. And get this phenomenon usually pops up in a totally different area of math.
Okay, this is where I start to get a little lost.
Yeah.
But also very intrigued.
It's like, those old mystery novels
Yeah.
where there's a secret passage connecting 2 rooms. You'd never expect them to be connected, but there it is.
I'm starting to see where you're going with this.
The Quillen-Lichtenbaum phenomena, it's kind of like that. It's about these unexpected relationships between different ways of studying shapes, particularly in the world of K-theory.
So it's like this secret passage that no one knew about.
Exactly. And Elmanto and Riggenbach, they're showing us that this passage, it also leads to the world of p-adic numbers.
That is kind of mind-blowing when you put it like that.
It really makes you wonder what else is out there. What other connections are waiting to be discovered?
It's like we're only just scratching the surface.
Exactly. And that's what gets mathematicians so fired up about these discoveries. Because it suggests that there's something much deeper, more fundamental going on. We're just starting to glimpse it.
Okay, so how did they even find this connection in the first place? We've talked about p-adic numbers, those perfectoid rings, and now this Quillen-Lichtenbaum phenomena. What other tools are in their mathematical toolkit?
Oh, there are a few more key players. One of them is called topological cyclic homology, or TC for short.
TC, got it.
Think of TC like, imagine you have this incredibly powerful microscope. It lets you study shapes in a very abstract mathematical space.
Okay, so it's like a super-powered microscope for math.
Pretty much.
I like it.
And then they also use the Segal conjecture.
The Segal conjecture, what's that?
It's this famous prediction in mathematics. It acts as a sort of guiding principle for their work.
Okay, so I've got TC, our mathematical microscope, and they're using it to examine this p-adic unit disk, all through the lens of the Segal conjecture. Am I getting that right?
You're getting on quick.
I try.
Now, their big aha moment, their breakthrough, that came from how they actually proved their results.
How'd they do that?
They used something called the motivic filtration.
Motivic filtration. Okay, now you're just messing with me, right?
Not at all. It's a real thing, I promise.
Okay.
Think of it like, you know those huge Lego structures, right?
Yeah, like the Millennium Falcon made of a million pieces.
Exactly. So the motivic filtration, it's like having this special tool. You can carefully take apart this massive Lego structure, brick by brick. And as you take it apart, you start to see, okay, so that's how this piece fits into the whole.
So they use this motivic filtration to sort of dissect the K-theory of the line over the p-adic unit disk.
You got it. They broke it down into these smaller, more manageable pieces. And that's where they saw it, the link to the Quillen-Lichtenbaum phenomena.
That's incredible. They saw this connection by carefully taking apart this abstract mathematical structure.
It's like finding a hidden message.
Yeah.
You know, buried deep within the structure itself.
Okay, so this is all incredibly cool, but I have to ask.
What's that?
Why should someone who's not, a mathematician, why should they care about any of this? What's the significance beyond all this abstract math?
I love that question. Because it might seem like this research, p-adic numbers, K-theory, like it's all just living in this theoretical world.
Right.
But it's actually laying the groundwork for some really big breakthroughs down the line.
Okay, give me an example.
Think about the digital world, right?
Okay, yeah.
Encryption, computer graphics, even artificial intelligence. They all rely on advanced mathematics.
So this research is kind of like investing in the future of those fields.
Exactly. We're talking about the fundamental building blocks of math here.
Building blocks. Got it.
This deeper understanding of p-adic numbers.
Ooh.
It could lead to more secure ways to encrypt data.
Oh, wow.
New ways to compress data. Even breakthroughs in how we understand these massive data sets.
Yeah.
It's hard to say exactly what the future holds, but that's part of the excitement, right?
It reminds me of like when physicists were first figuring out the nature of light. No one could have predicted that it would lead to things like lasers and fiber optic cables.
Exactly. Back then, those would have sounded like science fiction.
Exactly. But the fundamental research made it all possible.
And beyond the potential applications, this paper, it highlights something truly beautiful about math.
What's that?
The interconnectedness of it all.
What do you mean?
It's like math is this giant tapestry, right?
Okay.
And we're all just looking at little pieces of it. But every now and then, we discover a new thread. And suddenly, we see how these seemingly unrelated parts are connected.
So Elmanto and Riggenbach, they found one of those threads.
They did. It makes you appreciate the elegance, the unity of math. It makes you want to keep exploring. See what other surprises are out there.
It definitely leaves me wanting to learn more. So if our listeners are feeling adventurous, where can they go to dive deeper into this?
The paper itself is a great place to start. It's called On the K-Theory of the p-adic unit disk. You can find a link to it in the show notes.
And on that note, we'll wrap up this deep dive into the world of p-adic numbers, K-theory, and the incredible discoveries of Elmanto and Riggenbach. As always, thanks for joining us, and until next time, keep those minds curious.
Ever get that feeling like we're only kind of just scratching the surface of what numbers can actually be? Today, we're way beyond the familiar.
Okay.
We're diving into the world of, p-adic numbers and their role in this really fascinating area of math research. It's called K-theory.
Yeah, it's a bit like we're discovering the secret passageway that leads to like a whole new wing in a house that you thought you knew, right?
Right, yeah.
We're used to numbers we can count with or those we can like represent on a number line.
Yeah.
But these p-adic numbers, they offer a totally different perspective on them, a totally different way of looking at them.
Okay, so let's unpack this a bit. For those of us who, maybe aren't mathematicians.
Right.
What exactly is a p-adic number?
Okay.
And why should we care?
Yeah. So imagine you're trying to like analyze a mosaic, right?
Okay.
But you're focusing on like each individual tiny little tile.
Okay.
That's like our familiar number system. P-adic numbers, on the other hand, those are like if you were to step back and appreciate the patterns and the structures of the entire mosaic, but in a very unique way. They help us see these like relationships and connections that we might miss otherwise.
So it's about seeing this bigger picture, but through this like special lens
Exactly.
that reveals these hidden connections.
Precisely. And that kind of leads us very nicely to the work of these mathematicians, Elden, Elmanto, and Noah Riggenbach.
Yeah.
Their research focuses on a very specific mathematical object. It's called the p-adic unit disk. And it's this really, it's kind of like a playground for exploring these p-adic patterns, these p-adic numbers.
Mm-hmm.
Their paper digs into the K theory of this object.
Okay.
Essentially trying to map out its underlying structure, right? Like, how is it actually put together?
Okay, so K theory.
Yeah.
It sounds pretty technical.
It sounds very technical, but it doesn't have to be.
What's like the gist of it if you had to kind of break it down?
Think of K theory as like a really, really precise, fine-tuned tool that mathematicians use to sort of analyze the fundamental building blocks of these mathematical objects, right?
Right.
It's like a blueprint, right?
So Elmanto and Riggenbach are basically trying to decipher the blueprint of the p-adic unit disk.
Yes.
Using K theory as like their guide.
Exactly.
Like their map.
And what they found is really, really interesting. That's where you left us hanging. Yeah.
What kind of surprises did they uncover in this like exploration of the p-adic unit disk?
So they discovered this fascinating phenomenon.
Okay.
It's called Quillen-Lichtenbaum behavior, and it's within this p-adic unit disk.
Okay, I'm going to need a little help understanding what exactly that means.
Yeah.
Quillen-Lichtenbaum behavior sounds pretty intense, even for the world of, advanced mathematics.
Yeah, yeah. It might sound a little intimidating, but it's really all about connections. Essentially what they found was that this p-adic unit disk, it's deeply, deeply connected to what's called its K1 localization.
Okay.
And this K1 localization is it's basically another mathematical object, right?
Okay.
It provides a different perspective, but it's on the same like underlying structure.
So it's okay. So it's like, are we going back to our like secret passageway?
You can, yeah.
Okay. So we go through the secret passageway. We end up in this secret room.
Right.
But this secret room is like a mirror image of the first room, but it's seen through, like you said, a different lens.
That's a really good way to visualize it. Yeah. And the K1 localization, that acts as that lens, right?
Okay.
And what makes this discovery so significant is that this kind of connection, it wasn't really expected.
So they were surprised.
It was a surprise. They were surprised. Yeah, it really challenges some existing assumptions,
Mm-hmm.
And what this does is it opens up all these new avenues of research in p-adic K theory. It suggests that there's this deeper level of order and symmetry that maybe we didn't quite fully grasp before.
It's like we were realizing that the blueprint of that house that we were talking about, it's even more intricate and more elegant than we initially thought.
Exactly. Yeah, and to add like another layer to this whole thing.
Okay.
The way that they actually proved this connection, it's quite ingenious.
Okay.
What they did is they used this well-established mathematical principle. It's called the Segal conjecture.
Okay.
And they used it in a totally new way.
So they took this tool that mathematicians have been using, and they're like, but what if we use it over here?
Exactly.
In this p-adic world?
It's like they're saying, we've got this tool, it works great over here. What if we try it in this new unexplored territory?
Okay.
And it worked.
Wow. That's amazing.
Yeah, they essentially extended the reach of this Segal conjecture, showed its relevance in this completely different context, the context of p-adic numbers.
Yeah.
And that is a significant achievement in itself,
This is kind of reminding me of, those scientific discoveries that, seem super theoretical at first.
Right.
But then, down the line, they end up having these, huge implications.
Yeah.
Is that the case with these findings as well, do you think?
You're on the right track. So while this work is primarily theoretical, understanding the structure of this p-adic unit disk and its K theory has potential ramifications in other fields. This is not just some isolated thing, right? This is something that could have legs.
You're saying this deeper understanding of the p-adic unit disk could have implications beyond just, the world of pure mathematics.
Yeah, yeah. It's still early days.
Okay.
But these findings, they could have connections to areas like number theory.
Okay.
Which is, that deals with the properties of numbers.
Right.
And even potentially theoretical physics.
Right.
Which is, trying to understand the fundamental laws of the universe.
So you're saying the hidden patterns that Elmanto and Riggenbach are, like, revealing might actually offer clues about, like, the fabric of reality itself.
It's exciting to think about.
That's pretty mind-blowing.
It is. It is. The connections between these, like, seemingly abstract mathematical concepts and the physical world, they can be really profound.
Absolutely, yeah. What about, like, the future of this research?
Yeah.
What are some of the big, like, open questions that mathematicians are, like, grappling with in this field?
So Elmanto and Riggenbach's work, it's opened up all these, like, intriguing pathways, right, for, like, further exploration.
Yeah.
And one area of focus is generalizing their findings.
Okay.
So they focused on a very specific kind of p-adic unit disk.
Right.
But there are tons of variations and generalizations of this object.
All right.
Mathematicians are really interested in kind of exploring the K-theory
Oh,
of these variations, seeing if similar patterns and connections emerge.
So it's like they've illuminated one corner of this vast and intricate mosaic.
Exactly.
And now mathematicians are, like, eager to see what other patterns and connections are, like, hidden within it.
Yeah, it's a great analogy, and the tools and the techniques that they've developed, like their innovative use of the Segal conjecture,
right?
That's likely to play a key role in these future explorations.
I always love it when, like, a deep dive leaves me with even more to, like, ponder and think about. Like, it's clear that the world of p-adic K-theory is like full of mysteries, just waiting to be, like, unraveled. So, I want to thank you for taking us on this fascinating journey.
Of course.
It's definitely given me a new appreciation for kind of like the hidden depths of mathematics.
It's always rewarding to share these really fascinating areas of research with people and just highlight, like, the power and the beauty of mathematical exploration.
Absolutely.
Math can be beautiful.
Yeah, for sure. And for our listeners, if you're eager to explore this topic further, and we know you are, we'll be sure to include a link to Elmanto and Riggenbach's paper in the show notes. Until next time, keep those minds curious. Ever get this feeling like math is kind of like, I don't know, magic? Like, mathematicians are out there with their equations unlocking secrets of the universe.
It does have a certain mystique to it.
Well, today we are diving deep, and I mean deep, into a paper that feels a bit like a mathematical spellbook. It's all about using these things called p-adic numbers to uncover hidden patterns in a field known as algebraic K-theory.
Ah, yes. The paper by Elden, Elmanto and Noah Riggenbach on the K-theory of the p-adic unit disk. A fascinating read.
Okay, gotta be honest, that title makes my head spin a little.
It's a mouthful.
It is. So, p-adic numbers. I've heard the term thrown around, and I know they're not your average numbers you'd find on a ruler. What makes them so special?
Imagine a number line, right? But instead of closeness being about how many, like, inches apart things are, it's about divisibility by a prime number.
Okay, now you're just messing with me.
Not at all. Think about the number 7. In the world of p-adic numbers, two numbers are considered close if their difference is divisible by a high power of 7.
So, it's like, instead of cozying up to 0 on the number line, we're trying to be best buddies with multiples of 7.
You've got it. And the reason mathematicians get excited about these p-adic numbers is that they act like a new lens for looking at mathematical problems, especially in this field called algebraic K-theory.
Right, algebraic K-theory. You've mentioned it a couple of times now. Before we spiral down the rabbit hole, can you give us the quick and dirty, what is it and why should we care?
Imagine wanting to understand the shape of, say, a sculpture. Algebraic K-theory is like studying that sculpture, but instead of using your eyes and rulers, you're using algebra equations, groups, those sorts of things.
So it's like understanding something's shape by, I don't know, analyzing the shadows it casts, getting at its essence indirectly.
A very poetic way to put it. And what this paper does is show how p-adic numbers, through this lens of algebraic K-theory, help us understand this other tool called topological cyclic homology.
TC. Sounds kind of sci-fi, if you ask me.
It does, doesn't it? But it's a way mathematicians break down complicated shapes and spaces into smaller, more understandable pieces.
So like taking apart a clock to see how the gears mesh.
Precisely. And what Elmanto and Riggenbach do in this paper is show us a surprising connection within TC, something called the Quillen-Lichtenbaum phenomena.
Quillen-Lichtenbaum phenomenon.
Yeah.
Yeah, definitely getting wizard vibes now. What makes this discovery so mind-blowing?
Imagine exploring a giant castle, right? And you stumble upon this hidden passage connecting two rooms that seemed totally separate before. That's what this discovery is like. It makes calculations that were incredibly complex before much simpler, like finding a shortcut through a dense jungle.
So those mathematicians stumbled upon a mathematical cheat code, basically.
You could say that, and they illustrate this with a specific example involving rings.
Hold on, rings. Like the ones you wear on your finger.
Not quite the same thing. In mathematics, a ring is a set of numbers with specific rules for addition and multiplication. They're like building blocks for more complex ideas.
So rings are like the Lego bricks of abstract math.
Exactly. And what this paper does is show how p-adic numbers, through that Quillen-Lichtenbaum thing we talked about, give us new tools to study those building blocks.
Okay, my brain is officially doing backflips. We've got p-adic numbers, this TC thing, rings as Lego bricks. How does it all fit together in this paper?
One of the cool things Elmanto and Riggenbach do is use p-adic numbers to connect two seemingly unrelated ideas in algebraic K-theory.
Unrelated ideas. Ooh, I love a good mystery. Hit me with it.
Have you ever played with clay?
Who hasn't?
So there are these things called NK groups. They help us understand how you can mold and shape that clay, how you can twist and stretch it while still keeping some of its basic properties.
But like how much you can push and pull the clay before it loses its shape completely.
You got it. Now imagine shining a special light on that clay sculpture to reveal its contours, its hidden structure. That's kind of what symptomic cohomology does.
Okay, so NK groups are about the moves you can make with the clay. And symptomic cohomology gives you a glimpse of its blueprint. And p-adic numbers are the key to seeing how these two things are connected.
Exactly. The paper shows how p-adic numbers create this amazing dictionary between those two concepts.
Wait, a dictionary? You're saying that understanding the p-adic side of things can tell us something about both the flexibility and the structure of a mathematical object.
It's like realizing that the way you knead bread dough actually influences the pattern of those air pockets inside, something you wouldn't necessarily guess just by looking at the finished loaf. This paper suggests that p-adic numbers might help us make those sorts of unexpected connections in other areas of math, too.
That's wild. Okay, so far we've got these p-adic numbers, TC, rings, NK groups, and even symptomic cohomology. Before we get too lost in the mathematical weeds, what's the main takeaway our listeners should remember from this p-adic adventure?
Even in the super abstract world of mathematics, there are these beautiful, often unexpected connections just waiting to be found.
It's like we've been wandering through a dark forest, and suddenly, p-adic numbers have illuminated a hidden path.
And like any good exploration, this paper leaves us with even more questions than answers. It makes you wonder.
What other mind-blowing connections are hiding out there in the mathverse? Just waiting for the right tools to, shine a light on them.
That's the question, isn't it? This paper focused on a specific type of curve, but what if we use these p-adic methods on even weirder, more complex shapes?
It's like we've found this little peephole into a secret garden, but we can only see a tiny fraction of what's really out there. What if we could find the key and open the whole door?
And that's the beauty of mathematics. Every time you enter a question, it's like 10 more pop up in its place. It's all about the thrill of the chase, connecting the dots, finding those aha moments.
So for anyone listening who might be feeling like, whoa, this is way too abstract for my taste, just remember this. Math isn't just about crunching numbers. It's about that sense of wonder. It's about uncovering these hidden patterns, these connections that make you go, no way, that's so cool.
It's about looking at the world, even the parts that seem totally abstract, and asking, what if? What if we could use these crazy p-adic numbers to unlock even bigger secrets about, well, everything?
It's like those mathematicians who first started playing around with p-adic numbers. They stumbled upon a hidden doorway in the universe of numbers. And now, thanks to papers like this one, we get to walk through that doorway and see what's on the other side.
And that's the thing, isn't it? We have no idea what we might find. It's a journey of discovery that never really ends.
So well said. And it's a journey anyone can be a part of. So keep exploring, keep those questions coming, and who knows? Maybe you'll be the one to make the next big mathematical breakthrough. Thanks for joining us on this deep dive into the world of p-adic numbers and algebraic K-theory. Until next time.